Let's start our lecture today. So in the last lecture, we have been talking about several approaches for solving Markov games. We talk about the first approach, that is we combine the classical normal form-based normal form fast response based algorithm plus single agent reinforcement learning. Although the algorithm is quite intuitive, but there isn't like any strong theoretical guarantees or principle manner we can prove for this class of algorithm. Actually, there are some indications where this type of algorithm may not be very efficient in solving Markov games. Then we resort to the second approach where we talk about the reinforcement learning based approach. We're essentially just directly doing value iteration dynamical programming. We do the Nash value iteration. So we talk about our previous methods we have in several different settings, that is in the generative model. And in the end of very last lecture, we talk about the exploration scenario. So we talk about the optimistic Nash value iteration. Okay, this is like an online setting. Okay, and we end with explaining what is optimistic Nash value iteration algorithm, which essentially is doing Nash value iteration algorithm with slight modification that we need both upper bounds and lower bounds. And when we have upper bounds and lower bounds, we're now doing the general sum games. So we need to compute a CCE instead of a Nash because the Nash equilibrium of CCE is a PPAD hard to compute. So it's not computationally efficient. So we just left with the only thing that we haven't talked about the guarantees for this Nash value iteration algorithm. So this is what we will provide today. So the guarantee says with high probability, optimistic Nash value iteration finds an epsilon approximates Nash equilibrium. Just remember the epsilon approximate Nash equilibrium is defined in terms of duality gap. In the following number of episodes in O tilde, episodes is how many games you need to play. That is h cubed, again, is some polynomial dependence on the horizon, and a state dependence, S, this is a tabular setting, times A and B over epsilon squared episodes. Okay, and I think the most important thing that makes this different from the single agent guarantee is this is the number of actions of the max player. And this is the number of actions of the mean player. So you can think, although we need to use a new mechanism to design an algorithm, but in the end, in terms of sample capacity, how many samples we need to find the optimal policy, where here the optimal policy is Nash equilibrium. It turns out we just replace the number of action of the single agent scenario by the product of the action, which is the total number of action combination of the two player. Okay. I think the most important thing about this theorem is because like in the previous case, like in the first class of algorithm where we combine batch response-based algorithm with single agent and reinforcement learning, we're saying like it's likely we cannot get any like efficient guarantee because the policy is like policy space is huge and those BR-based batch response-based algorithms are not very efficient. And the most important thing here is once we resort to this like reinforcement learning-based algorithm, we can actually conclude that optimistic Nash value iteration is able to find epsilon approximate Nash equilibrium in polynomial times and samples. Okay. So this part is the important thing. Now we do have a polynomial time and sample algorithms. And the other thing you might wonder is this seems like if you look at the sample complexity, this seems like pretty straightforward. As we said, we just replace the single agent number of actions by like the total number of action combinations by the two-player. But in the game, we might have like a more structure, like we want to find Nash equilibrium. So natural question is whether this kind of sample complexity is optimal. So it turns out at that time it was unclear because the basic information theoretical lower bound one can prove is actually something lower. So the information theoretical lower bounds one can prove is something like this. Something like omega to the h cube s max AB over epsilon square. Okay, so this is like something more interesting happen in the game, that we actually don't need to pay the, in the lower bound at least, we actually don't need to pay the, like the product of the action. In this complexity, we only need to pay the max number of action of both player. So this leads to actually some unique challenges in the multi-agent reinforcement learning we want to talk about. So far it seems like we just directly borrow what we have for single agent reinforcement learning while replacing the maximization by essentially just replace the maximization by finding Nash equilibrium and solving the minimum max. And other than that, we didn't do too much. Like CCE is a little bit trick, but other than that, we didn't do too much. Okay. So now the first unique challenge we have that basically does not appear in a single agent reinforcement learning is so-called the curse of multi-agents. So basically, we can already see some clue in this like two-player zero-sum game setting. So the sample complexity scales with something like the product of number of actions. Okay. This is we already showed it for the two-player scenario. In the multiplayer scenario, you can essentially extend this kind of algorithm to the multiplayer Markov game. We'll talk more later. But basically, you can imagine if we just continue using this class of algorithm directly using dynamic programming combined with like Nash solver, we will end up with some complexity that is omega to the product of I from 1 to m, ai, where m is the number of player. Essentially the product of the number of action for each player. And this is roughly something omega to the a to the m. Okay. If we have m player. This is like the number of players. So the bad thing about this is you can clearly see this grows exponentially in m. In m, the number of players. The reason for this is, remember for when we're doing this kind of Nash value iteration, we kind of have a joint Q value. And the size of joint Q value, whenever we want to estimate something like that, it's like Q, S, A1, dot, 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 till AM. So if in a tabular setting, essentially we need to remember all the values for different action combinations. So basically the size of such a Q table is omega S times product of AI. So essentially whenever we want to estimate such Q value, joint Q value, we kind of like we need to pay something exponential in M. So the question is, can we actually go beyond this type of algorithm and can we achieve some poly-M, some complexity? So this is the first challenge, essentially also related to this complexity, whether we can improve from AB to max AB, or can we improve from like a to the power of m to something polynomial in m. Okay. And the second unique challenge in this scenario is called the design of decentralized algorithm. Also, just recall that in like a VIUCB or Nash value iteration, we need kind of like maintain a centralized solver. To compute the joint Q value, okay, something like a Q upper bar, S A1, A2, Q lower bar, SAB. Similarly, when we like extend this Nash value iteration to multiplayer, like this is like still, whenever we doing this like joint Q value thing, it's still a centralized algorithm in terms of everyone need to communicate and eventually compute some joint Q value. A lot of times we actually favor some decentralized algorithm. So decentralized algorithm is somehow very different from this style of like a centralized solver and compute something jointly. And decentralized algorithm is something much favored in practice, is something like this. Ideally, a decentralized algorithm means like each agent will just runs her own algorithm independently using her own observation. As if in a single agent setting. So why we're interested in such kind of a decentralized algorithm? There are a couple of reasons. First is this kind of algorithm is definitely easier to implement. In a sense, we just need to design a single agent algorithm, and for each player, like for each agent, how to learn, and then we just copy it for multiple different agents. So it's very easily to scale up to multiple different agents. We don't even need to write some new code. Second thing, this is also more versatile. If we have such a kind of algorithm, means this algorithm like work in some strong sense, in the sense like it's basically doesn't really care about what other player is doing. So it will be agnostic to the action of other agents. Finally, it just has less communication. And because there is no centralized solver, each agent just run their own algorithm, so we don't really require a lot of communication. So actually, there's no communication. So this is just reason a lot faster. And if you ask game theorists why we care about this decentralized algorithm, they would even argue like this is just like real life. Like if you are reinforcement learning agents, like you learn how to behave well in this world, you are essentially doing that kind of decentralized algorithm because you will make your own decision and based on your own observation, and basically this is like what you're doing. So once we talk about these two challenges, I guess immediately we can ask the main question in multi-agent reinforcement learning that is like very unique, very different from single-agent reinforcement learning is can we design decentralized multi-agent reinforcement learning algorithm that breaks the curse of multi-agency. So we want to basically solve two challenges simultaneously. This will be the main question we're going to deal with in this lecture. Okay? So before we talk about how we're going to solve this problem, we first, I want to talk a little bit more about the formalism, because now we're talking about like this recursive multiplayer and decentralized algorithm. It's very natural to consider the general sum, like multiplayer general sum game, that is like a beyond two-player zero-sum scenario. So I just want to briefly like talk about the formulation of a general sum game, Markov game, which is very similar to the two-player scenario. So just be quick about all things. So a general sum Markov game is, again, we have a bunch of things. That is, we have a set of states. And now, because we no longer just have like two players, so we have a bunch of action sets, where suppose we have M agents, where AI is the action set for ith agents. So we have M different action sets. And the transition, we just have a single transition. Reward, we have M different reward. Remember, now it's no longer a zero-sum game, so each player's utility can be different. And H. Okay, so I think those are pretty straightforward, and the transition is specified as PSH plus 1 given SH, and sometimes I will just use AH and with vector notation, where this is like a joint action. Where the A vector H means we have action of the first player, action of second player, and also we have action of M's player. So we just have action of all the player combined together, and we denote it as this A vector notation. And similarly for this reward or utility, we also denote it as RIH, SH, AH, and with this vector. So basically the utility is going to depend on the current states and the action of all players. But the utility is different for different players. So this specified the reward or utility for the ith player. Okay. Any questions? And H is just horizon, S is the set of states. So we can also define the Markov policy for the ith player. It's just defined as a collection of pi ih, h from 1 to capital H. So again, it's a policy, one policy at each step, where pi ih is a map from only states, so local states, and map is to a distribution over the action set of his own action. So over the distribution over the actions in the AI, that is action set for the ith player. Similarly, we can also talk about the value. So those are just very similar stuff. And VIH over pi, but here pi is the joint policy. Is the, again, expected cumulative reward going to received by the ice player if following the policy pi. Okay, so VI pi is equal to the expectation of all the future reward for ice player. Okay, similarly, you can also define a Q value in this way. I say this is a V1 as well. So after we talk about the policy and values, we can talk a little bit about the objectives. Remember, in the game setting, we talk about the equilibrium is something we want to find. So for multiplayer general sum Markov game, we can also define a Nash equilibrium. Nash equilibrium is, again, defined as a product policy. Pi star is equal to something like a pi 1 star, pi 2 star, till pi m star. That is, each player will choose a policy, will choose a distribution over action, and those distributions are kind of like independent. They are not correlated. So this is called product policy. And we say this is a Nash equilibrium. If no player has incentive to deviate from her current policy. In which sense, in the math, we can say we have a value for the ice player. If we look at the pi I cross pi minus I star, for any pi I, this is essentially my opponent, all my opponents still playing this Nash equilibrium while I'm deviating from my policy. So I'm guaranteed I won't gain anything. That is, my value by deviating my current policy will actually smaller or equal to if I just stick with the Nash equilibrium. sorry, this is like the value of ice player at the first state. Okay. This is, you can also see, just put state 1 here, state 1 here. So we kind of know that even in a special case, of normal form game, we talk about in the last lecture. We know that finding Nash equilibrium in the general sum game is actually PPAD hard. This, as we said in the last lecture, like there is no polynomial algorithm that is able to find such a Nash equilibrium for general sum game. So a lot of times we used some surrogate type of equilibrium. We kind of like already mentioned the concepts in the last lecture. That is, we will use the CCE, correlated equilibrium, or coarse correlated equilibrium. So there's some surrogate. They're like correlated equilibrium. In short, we call it CE, and there's another kind called a coarse correlated equilibrium. CCE. So what is the correlated equilibrium, or what is so-called a correlated policy? So we kind of like look at the difference between product policy and correlated policy. So for the product policy, or like what a Nash equilibrium requires, it's kind of like we first have a bunch of a policy that pi1 is mapped from S to distribution of A1, and we have pi m that is mapped from state to distribution of AM. So when we do this map, there are a lot of randomness in choosing A1 and AM. So when we call the product policy, that we directly put pi, that is equal to pi1 product with pi2 product with pi m, we're saying essentially we make those randomness independent. That is how you're going to flip the coin and choosing the A1 in this probability, and how you're going to flip the coin and choose the AM in this probability is independent. This is called product policy. While correlated policy can be something slightly different, which is very useful in the general sum game because it's not necessarily just competitive, it can be like cooperative. So that's why in general it might be helpful to share the randomness. So correlated policy in general is just a single map that maps from S to the probability distribution over all the joint action space. So it can have a very complex distribution. That, for example, I use 1/2. For example, if A1 and A2, all the action set is like have two actions, 0 or 1. So this correlated policy can deploy some policy that with 1/2 probability, I will choose action 1, 1, 1, 1, 1. And with 1/2 probability, I will choose action 0, 0, 0, 0, 0, 0. This is a correlated policy. Well, in the product policy, you can never do that because product policy, each player, they need to like choose a Bernoulli. So you won't be able to have like a 1/2, 1/2 as all 1 or 0. As we mentioned, in general sum game, it might be beneficial to sometimes consider this correlated policy because the general sum can also have like a cooperative part, and a lot of times correlated policy makes sense. So while Nash equilibrium is equilibrium only developed for the product policy, so we can also have some correlated, like equilibrium defined for the correlated policy. So first is CE, and the other one is CCE. Okay. So CE is the correlated policy. Where no player can gain by deviating from her own strategy. If she can still observe her sampled action from the correlated policy. And we will talk a little bit more about what does this mean. Okay, and the CCE is basically the same kind of definition, and the only thing is he can no longer observe. Okay, so this can change to cannot. So let's just pass a little bit of what does this mean. So first, when we talk about equilibrium, it's very similar to a Nash equilibrium, where everything is about like if other players stick with the current strategy and I deviate from my current strategy, I won't gain anything. So the only thing a bit trickier about a correlated policy is there are two types of condition like when we deviate from my policy. One is like a CE, because this correlated policy, it needs to be implemented in the following way. That every time there might be a centralized player or whatever, a god, like first roll a dice, and roll a dice to something, and then the god will tell every player like what kind of action to play. This is like sampled action, joint sample action. So there are two types of things. One is if you deviate from like if you betray other player, if you deviate from your current policy, you can no longer observe the dice from the god. So you just completely dark. I no longer know what kind of randomness has been sampled. This is called a CCE. And on the other hand, if I betrayed and the god still give me the dice, like I still know what other player is going to play according to this randomness, this is called a correlated equilibrium. Okay, so there are two types of correlated equilibrium. I don't want to go formally about the mathematical definitions. If you're interested, you can free to look at the related literature or game theory like tutorial course about like how to formally define those two equilibrium. It's not necessarily used in this lecture, but I just want to talk about the intuitive concepts and what's the relation between those concepts. So as we mentioned last time, Nash equilibrium is a subset of CCE. It turns out for those three, Nash is the smallest set, and Nash is guaranteed to be CE, and CE is guaranteed to be CCE. Okay, and interestingly, the smallest set is PPAD hard, while everything else is in P, is in polynomial class. Okay, you can basically solve by linear programming for normal form game. So this is like a brief about formulation of like a multiplayer Markov game. So let's go back to our question where we want to design decentralized algorithm that breaks the curse of multi-agency. So now we talk about design of decentralized algorithm. The first thing we might think of is why not just everyone like run the single agent algorithm? Like, how about every player like, for example, we can run value iteration or run Q-learning, for example, like, let's say, we do independent Q-learning. Remember, this Q-learning is different from like value iteration where we look at the Q value of joint policy, because this is a joint action. This is like decentralized algorithm, so each player just run their own algorithm. So you just treat it as if like although other players are like changing, they just treat it as an environment and just run the Q learning that was only Q value that as a state and his own action. Okay. And this type of algorithm, as we mentioned earlier in this class, that one of the most important difference between single agent and multi-agent is opponents are not stationary. Okay, opponents are like changing, adaptive. So this kind of algorithm like treat opponents as stationary. Which is definitely incorrect. Okay, this is something you should not do because opponents are not stationary environment. They're like adaptive opponents. So far, like up to now, there's not any guarantees about like proving this type of algorithm could actually converge to any like meaningful objectives. And I think it's very likely you can easily construct some counterexample which says this type of algorithm would not work. So what kind of algorithm would achieve such kind of decentralized algorithm and also breaks the curse of multi-agency? Or you may think this kind of objective may even seems like very difficult to achieve. So it turns out in terms of game theory, like we said, we always start from the normal form game. So in the normal form game, there is some answer to such kind of algorithm. So such kind of problem. So we should start from there. So the whole idea in a normal form game to design this decentralized algorithm that will break the curse of multi-agency is instead of treating opponents as a stationary environment, I'm gonna design something for adversarial opponents. Okay, so this is big idea is called like no regret algorithm, which is very popular in this like a normal form game or in game theory literature. So the answer is basically just design so-called no regret algorithm. By no regret algorithm, we actually means we will basically achieve sublinear regret we already mentioned in our online reinforcement learning setting, like linear regret is like trivial regret. Sublinear regret is something like non-trivial. But the most important thing about this no regret algorithm is not only just achieving sublinear regret, but it's achieving sublinear regret against adversarial opponents. Okay, so this is the key part. So basically, we are saying like earlier, if we just treat the opponent as a stationary, this is like too weak. That won't be enough. And now if I just make an opponent stronger enough so that my algorithm even works for any opponents or even the adversarial opponent that adversarially like play against me, I can still work. And then this algorithm would guarantee to find something useful. So we'll see what kind of algorithm would achieve this type of guarantee, like no regret algorithm guarantee. So it turns out that there are a lot of algorithms that can achieve this, can be called like no regret or achieve sublinear regret. So I will just introduce one of the very like famous one. It's called EXP3 for multi-arm bandit. Okay. The reason we do it for multi-arm bandit with bandit feedback is because in normal form game, remember the normal form game is specified by a game matrix. So if we kind of like look at one player's perspective and treating other players as adversarial, then in that sense, from one player perspective, we're just playing like a multi-arm bandit. Okay, we're just choosing arm. The only thing is the reward is also going to be affected by other players. So the reward is kind of like adversarial. It's no longer stochastic. So the EXP3 algorithms works as follows: that in each round T, we will set some probability that mu ti just equal to some weights normalized by summation. So essentially for each action, we will have a weight. And this weights, normalized weights denoted the distribution mu t. So every time I will just, in every round, whenever I play, I play the multi-arm bandit problem, I will draw the action, AT, randomly according to the distribution RT. A distribution mu t. And then we will observe the estimated loss which is we use LT hat to estimate the loss, where LT hat for action I is equal to LTI, the true loss we observe, and divided by the probability we play it, and times the indicator that I is equal to AT. Okay, that is if the action I is the action we play at round T, we will just use the observed loss divided by the probability to play that action. Otherwise, I will just always use 0 to estimate my loss. So the reason we do such an estimate is because you can easily verify that the expectation of the loss estimates of this can be looked at viewed as a vector, and this is ith coordinate. So the whole vector in the expectation is equal to the original loss. So this is like unbiased estimator, unbiased stochastic estimator of the loss vector. And finally, after we observe this estimated, we just set new weights. Wt plus 1 I is equal to Wt Wtj times exponential to the minus eta, some learning rate, and Lt hat I for all j. So the key update is essentially just this so-called multiplicative weights update. So every time this weight is related to the probability, how much probability I'm going to play the action j. So if the loss is large, I'm going to shrink this weight a lot. If the loss is small, I won't shrink this loss much. Okay, and this is basically the whole intuition about this algorithm. Essentially, you can think this algorithm just every time I receive some loss, I'm going to penalize this action, and how much weights are going to penalize. It depends on how much loss I observe. So eventually, if this arm has a very little loss, and eventually I won't shrink this weights by too much. If some arm has a lot of loss, and then I will shrink that arm by a lot, and eventually my distribution over arm will be more or less focused on those arms that has a very little loss. So you can think this is like a soft version of trying to be greedy with respect to the history. So very greedy with respect to history is just looking at the history and which arm performed the best. I'm just taking that arm. But this is essentially saying I'm gonna do some exponential weighting instead of just looking at which arm doing the best. So it turns out this simple algorithm is able to achieve the no regret guarantee. So the guarantee looks like the following, that we will see for arbitrary loss, like L1 till Lt. We have something like this. That's summation t from 1 to capital T mu t Lt subtracted by the minimum of A in A, summation t from 1 to capital T A Lt less equal to polynomial of A times t to the minus alpha. So whenever we have such a kind of guarantee, we say this algorithm is like a no regret algorithm. If some algorithm is like that, then we say algorithm is no regret algorithm. As we mentioned earlier, the important thing is the regret is sublinear. This is like t to the 1 minus alpha. And this is regret because mu t is the distribution essentially taken by the algorithm. Okay, the algorithm chooses to play according to mu t at t's rounds. So this is essentially the expected utility that's going to receive, expected loss that's going to received by the algorithm, and this is a minimum loss, like essentially the best loss you can achieve by playing a fixed action. And if you look backwards, that is in hindsight. We're saying like this is always like the regret type of guarantee. We look at those two differences. That is, what if I just always play some best action in hindsight, and how much regret I'm gonna suffer in total? And we're saying this need to be sublinear too. So basically, we say exp3 is no regret algorithm, is a no regret algorithm. because you can essentially prove exp3 satisfies such kind of guarantee and with alpha equal to 1/2. And one of the very important thing about this no regretta is kind of like we say, this actually holds for any adversarially chosen loss sequence. So this kind of like is very important in the multi-agent scenario because this loss vector, as we said, when we look at the normal form game, when other player are playing some policies, then look at the one player perspective, it's kind of like as if it's doing multi-arm bandit. But the only thing is this reward is not generating from some stochastic distribution. It's actually generating from some possibly adversarial stuff because other player play some, like you don't know what other player is playing. So this kind of guarantee is very important. And because the loss can be affected by other player, but this guarantee says whatever other player is doing, I don't care. I can always achieve this sublinear regret guarantee. So this is why this is like so important. And it turns out when we combine such a no regret algorithm, we can easily find a CCE or Nash. So the following claim basically can be easily shown by just definition. Okay. So if every player is running a no regret algorithm, they don't even need to like coordinate on what kind of no regret algorithm you learn. We say exp3 is one of no regret algorithm, but each player can just run different no regret algorithm, or they can run no regret algorithm with different learning rates, with different stars or something. As long as it's no regret algorithm, the following claim is true. Like in a two-player zero-sum game, we know the expectation if we sample this T uniformly. Okay, I think we just say we look at the average policy 1 over T summation tau from 1 to T, and this mu tau 1. And 1 over T summation tau from 1 to T mu tau 2. Basically, this is the action distribution by the first player and at tau's iteration, or tau's rounds. And if we just doing an average over the first player's distribution, and then we look at the average of the action distribution of the second player, we can prove this will converge to Nash equilibrium. Okay. Basically, by just manipulating this like no regret guarantee and like plugging this as an opponent strategy, and then eventually you're able to prove this kind of guarantee. And this is for two-player zero-sum game. So just know this is already very different from like where if we run single-agent Q-learning, we don't achieve anything. While here, if we run no regret algorithm, we can already find Nash equilibrium. And similarly, in the general sum games, we can do the following, that we will look at the average policy. Here is slightly different. We should not just look at the independently sum of each player's policy, but we will look at the joint sum of each player's policy. That is, at every step, each player's policy is independent. So mu tau 1 cross mu tau 2 So at every iteration, each player's policy is independent. But when we do the Cartesian product of them, do it as a product policy, and then we do an average over such kind of policy. And because this summation, this average, actually will introduce some correlation. Okay. So each summand is an independent policy, but when we do this mixture of this independent policy is no longer independent, it's no longer a product policy, it's become a correlated policy. So you can prove such a policy actually converges to CCE. And the most important thing, because for each player, they're just running like a no regret algorithm, and this A is the number of actions of the player. Of the player itself. Okay. Because it treats all other players within the loss, so this A is no longer the joint action, it's just the action of the player by itself. So in this sense, each player doesn't really care about how many actions other player has. And you can prove the sample complexity only scale with something very good. It's only actually O tilde max I AI. Okay. So if every player has the same number of actions, then they just scale with A. There is no dependence even with like the number of players in this type of algorithm up to some logarithmic factor. So basically in the normal form game, if we, after looking at all those kind of things, we know the answer is very simple. We just do no regret algorithm. As long as we can design some algorithm can beat adversarial opponents, then everyone just run this kind of algorithm, and then we will guarantee to find a Nash in two-player zero-sum, and to guarantee to converge to CCE in the general sum games. So finally, after we did so many preparation work, like to solve this type of problem, and we will extend from like normal form to Markov games. So we'll ask questions like, can we just run no regret algorithm for a Markov game? So basically, based on the same philosophy, if there are some no regret algorithm, we can directly just run it and we solve the entire problem. So it turns out, unfortunately, the story is more complicated than this, and unfortunately, the answer to this question is actually no. Okay. So by no regret algorithm to this problem, we do mean like something like if we can have some max pi and a summation t from 1 to capital T, and this is like a Markov game. Pi I cross pi t minus I, and subtracted by summation t from 1 to capital T, v1 pi t, smaller than some poly t. Polynomial times t to the 1 minus alpha. For adversarial opponents, basically any player can choose the policy for other player, choosing the policy of the opponents. So such kind of guarantee is basically saying, if my opponent is an adversarial, he just chooses whatever the player for the other policy for the other player, and this is the total expected utility I'm going to receive, total expected reward I'm going to receive, and this is like basically the best utility I can receive in hindsight if I'm always playing some fixed Markov policy. And I want to achieve some sublinear regret. And turns out this is actually unfortunately not possible. The reason is, again, comes out with this like a temporal correlation. Like a normal form game is just one-step game, so there's not much like a transition and state transition. So basically, everything can be done in that way. But here, because this is like a Markov game, this is again like a reinforcement learning. Everything that goes wrong is because we have this horizon edge. And it turns out if we want to have some no-regret guarantees for Markov game, you can no longer pay this polynomial. Like you have to pay something exponential in h. In this kind of regret guarantee. So that's why like if we just want to have some polynomial independence on everything else, this is not possible for Markov game. Okay, so till now you might think, okay, this seems like a very bad. Does that mean like for Markov games we can no longer design some decentralized algorithm or recursive multi-agency? So the answer is actually for that task we can indeed design some algorithm. So basically key observation here is the no regret algorithm. If we design no regret algorithm, we can imply finding Nash or CCE. That is, once we have designed this kind of algorithm, we can solve this problem. But this does not mean this task is hard, this task is also hard. This does not say that, because the reverse is not true. Like once we have some algorithm find Nash equilibrium of CCE, we may not necessarily be able to design. So you can think this is actually a harder task. So finding a no regret algorithm, because we want to beat against an adversarial opponent, this is like a very difficult task. While finding Nash or CCE is slightly easier than the no regret algorithm. So it turns out for Markov game, this is something you cannot do, but this is something you can do. So the key idea here is instead of like directly designing some no regret algorithm, we will bring no regret algorithm, this idea, like combine it with the dynamic programming to design some new type of algorithm that is able to like break a curse of multi-agency and like have a decentralized algorithm. Okay, so this is the next algorithm we'll introduce. It's called a V-learning algorithm. So you can see from the name, it's kind of like very similar to the Q-learning algorithm in the single agent reinforcement learning, but we will see what's the major difference there. So the algorithm, the pseudocode looks like the follows, that for k equal to 1 to capital K, we again first receive some initial states as 1. For step h equal to 1 to capital H, we do the following, that we take action. H, according to some policy patch we will compute later, and observe reward RH and the next states. sh plus 1. So the first step is very straightforward. It's just we take action and receive some samples. And we add a count. That is, this nh is the number of times observe sh. We set the count plus 1 because we now newly observe a new state sh. And then the key steps is the following two steps. The first one is we update the v value of the current states we observe. That we will, very similar to the q value, we're Q-learning doing the incremental updates. Here we're also doing the incremental updates, doing 1 minus alpha t, and alpha t is like the learning rates, vh sh plus alpha t rh plus vh plus 1 sh plus 1 and plus some beta t, where beta t is the bonus. So this step is very similar to the Q-learning steps. Well, the only difference is instead of updating the Q value, I'm only updating the V value. But there's a reason why we usually do Q-learning instead of a V-learning, like in a single region reinforcement scenario. Because if we only have the V value, we don't have the policy. If we have a Q value, we can know like we just do some greedy policy regarding to the Q value that taking the maximization of action for each state, then that can like generate a policy we can run. But if we only have the V value, we don't have any policy like from the value, so that's not enough. So that's why we have a second step that we will leverage the no regret guarantee. So what we will do is we will, in addition to just having V value, we'll calculate the policy we're gonna take for this sh states. And the policy is going to be updated by running an adversarial bandit algorithm. So because for Markov game, if we look at each state, for each state at every step, you can think it as like a bandit problem. And then for bandit problem, every time for updates, we only need to feed in what kind of action it takes. This is AH it takes, and what kind of loss or reward it receives. So it is something like this. It's RH plus VH plus 1, SH plus 1. So basically this step is the key step here. And we say for every state, maintain an independent adversarial bandit algorithm. Notice every state will run its own instance of like EXP3 algorithm, for example. And when we update certain states, and we will only activate the adversarial bandit algorithm of that states by pulling the arm A and getting this utility or like the loss, update the adversarial bandit algorithm. because this is decentralized algorithm, so V-learning is also a single agent reinforcement algorithm. So you can think this also would work for single agent setting. So we just quickly talk about the difference. So in terms of Q-learning, we maintain a Q value, and the policy is like the greedy respect to Q. Well, for V-learning, the major difference is now we no longer maintain a Q value. We only maintain a V value. So we are slightly weaker. We can no longer take the greedy action. So what we will do instead is we will do adversarial bandit, or like no regret algorithm. This is a state-wise no regret algorithm. It's not like overall Markov game no regret, but a state-wise no regret algorithm on states to compute the policy. Okay, so we just have a little bit finished. In the next lecture, we'll talk about the guarantee for the V-learning, and we'll wrap up the multi-agent reinforcement learning part. And we finally have one more lecture this week, and the next lecture we will compensate for a lot of sickness and cancellation. We'll probably have one more lecture, and for the remaining 2 lectures, we will talk about the partially observable reinforcement learning. Okay, yeah, thank you.